Hello students, welcome back to yet another session in unit number 3 and where we are continuing the magnetic refrigeration system. So this is the topic we have started in our earlier session and now we are continuing the same and we will be completing the same topic now in this session. And we have two more topics to deal in this unit that we will see in subsequent sessions. So these are the topics in unit number 3. We have vapor absorption systems, and then we have adsorption system, steam jet refrigeration system, thermoelectric air refrigeration system, and magnetic we have started in earlier session. Now we are going to complete this topic. And vortex tube refrigeration system, pulse tube refrigeration system. So these are the two more topics we have to cover, and we will deal these two in coming sessions, coming two more sessions. So now we will complete magnetic refrigeration system. So comparison between magnetic refrigeration and conventional refrigeration system. So here this is one simple comparison, the diagrammatic comparison. So here this is magnetic refrigeration. So in step 1, magnetize the solid, thereby increasing the temperature. So we are magnetizing this solid and we are increasing the temperature of this solid. So that is the first step, whereas here we are compressing the refrigerant and we are increasing the temperature. So this is the comparison between these two processes. And then in step 2, remove the heat with a cooling fluid. So hot fluid out and cool fluid in, and whereas here the removing the heat with a cooling fluid. So this is the condensation process. So fluid in and fluid out, and then we have the temperature, step 3, demagnetize and cool solid. So now we are almost taking out the solid object from magnetic field, and then it is nothing but demagnetization. Then now this solid is being cooled. So whereas expand the cool gas, so the expansion of the cool gas is through throttle or expansion device. And as fourth step, absorb heat from the cooling load. So now the heat is absorbed from the cooling load, and now cold fluid out and cool fluid in. So this is what this solid is doing, and this is nothing but the evaporation. So here the final stage of cooling process, and here the absorb heat from the cooling fluid. So now absorbing heat from cooling fluid. So this is the last step in conventional refrigeration system. So almost both are very similar in nature, and we can correlate this and we can easily remember these 4 steps. And with this diagram also you can easily explain both the types of processes. So now the magnetic refrigeration, the step 1 is magnetize the solid, thereby increasing its temperature, removing heat with a cooling fluid, and demagnetize and cool the solid, absorb heat from the cooling fluid. And conventional refrigeration system, the same steps, compress a gas, thereby increase its temperature and remove heat with a cooling fluid. And step 3, expand and cool the gas and absorb heat from the cooling fluid. And key differences, the process of compressing a gas and expanding the gas in conventional refrigeration is replaced by magnetization and demagnetization in magnetic refrigeration. So compression in conventional refrigeration occurs through the gas, while the magnetic refrigeration, a magnetocaloric material is used. So this is what MCE, magnetocaloric effect, so that we discussed in earlier session. And here the compression in conventional refrigeration occurs through the gas, while in magnetic refrigeration a magnetocaloric material is used. So this is the key difference between these two processes. So magnetic refrigeration challenges heat transport in magnetic refrigeration. So unlike in gaseous refrigerants where turbulent motion transports heat quickly, the heat transport in magnetocaloric materials is slower due to molecular diffusion. To overcome this limitation, porous structures are designed to speed up the heat transfer in the material, and cascade or regenerative magnetic refrigeration designs may be needed, especially in larger systems, to improve heat transfer. So, system components, conventional gas compression refrigeration, so driven by continuous repeating of four basic steps, that is compression of gas and heat rejection condenser, expansion of gas, heat absorption evaporator, magnetic refrigeration. Here the compression is replaced by adiabatic magnetization and expansion is replaced by adiabatic demagnetization, and a conventional vapor compression refrigeration cycle and magnetic refrigeration compression. So in magnetic refrigeration, compression is achieved adiabatic magnetization and expansion is replaced by adiabatic demagnetization. So these are the system comparison. So components of magnetic refrigeration. So components required for construction: first magnets, hot heat exchanger, cold heat exchanger, drive, magnetocaloric wheel, and magnets. Magnets are the core elements in the magnetic refrigeration system, and they generate the magnetic field required for the magnetocaloric material, enabling it to either gain or lose heat. So here this process is essential for transferring heat between the material and the surrounding environment or the space that needs to be cooled. So hot heat exchanger. So hot heat exchanger plays a critical role by absorbing heat from the magnetocaloric material and releasing it into surroundings. So surroundings. This process is vital for maintaining the efficiency of the heat transfer and for enabling the cooling cycle to continue effectively. So this is the hot heat exchanger, and we have cold heat exchanger. The cold heat exchanger is responsible for absorbing heat from the space that needs cooling and transferring it into the magnetic material. This ensures the effective absorption of heat, assisting the refrigerating cycle to lower the temperature of the targeted environment. So the drive provides the necessary rotation of the system, ensuring the proper handling of heat. It directs the flow of heat in the desired direction, maintaining the balance and functionality of the system throughout the cooling process. So magnetocaloric wheel, and the magnetocaloric wheel is structural component of the entire system, and it physically connects the two magnets, ensuring that they work together properly. This wheel enables the synchronization of the magnetic field and the magnetocaloric material, facilitating the heat exchange process. So requirements for practical applications: limited selection of magnetic materials. A small number of magnetic materials exhibit the large enough magnetocaloric effect and required for practical refrigeration systems. The search for ideal materials often focuses on rare earth metals, either in pure form or allied with other metals. So magnetocaloric effect. The magnetocaloric effect is an intrinsic property of magnetic solids where the material's temperature changes as it is magnetized or demagnetized. So this effect is maximized when the material is near its magnetic ordering temperature. So magnetic entropy and adiabatic temperature changes. So the degree of magnetic entropy and associated temperature changes are strongly dependent on the magnetic order process. So the magnitude of these changes is generally small antiferromagnets and ferrimagnets and spin glass systems. The effect is most significant in ferromagnets undergoing a first order magnetic attraction where the material exhibits the largest temperature change. So requirements for practical applications, influence of external factors, so crystalline electric fields and pressure can influence magnetic entropy and adiabatic temperature changes significantly. Gadolinium is commonly used as refrigerant due to MCE properties, magnetocaloric properties, typically producing a 3 to 4 Kelvin per Tesla change in temperature. So the recent research, if you see, the materials such as GD5, SIX, GEX, LA, FE, SI1 and X, and 13HX, and MNFE, P1, ASX allies are among promising candidates for managing magnetic refrigeration due to their giant magnetocaloric effect. So GMCE. So giant magnetocaloric effect is another effect where the magnetocalorific effect is very high, and magnetic material behavior. So gadolinium and its allies, if you see, GD gadolinium exhibits one of the latest known magnetocaloric effects and making it a key material in magnetic refrigeration designs. It undergoes a second order phase transition at the Curie temperature 294 degree Kelvin, a key feature for materials used in refrigeration, and gadolinium has been used historically but faces limitations such as high cost and susceptibility to oxidation and behavior in magnetic fields. The process shown in figure demonstrate how gallium alloy heat up when inside a magnetic field and lose thermal energy by radiation, exiting the field cooler than when it entered. So this diagram we see in a coming slide. So here magnetocaloric effects materials for future applications. Some promising categories of magnetocaloric materials include binary and ternary intermetallic compounds, gadolinium, silicon, germanium compounds, and magnites, lanthanum, iron based compounds. So manganese, antimony, arsenide. So iron, manganese, arsenide phosphides. So amorphous fine mesh type alloys, a very recent development. So this is coming up now, and gadolinium remains a fundamental material through new materials with higher efficiency at room temperature are being explored, such as GD, SI, GE alloys. So regenerators, importance of heat transfer. The magnetic refrigeration requires excellent heat transfer from the solid magnetocaloric material. Efficient heat transfer is crucial for maintaining the effectiveness of the cooling cycle, and porous materials and regenerators. Here, regenerators are structures that employ porous materials to enhance heat transfer by providing a large surface area for interaction, and regenerator geometries. So common geometries are regenerators in magnetic refrigeration systems include tubes and other similar designs that optimize heat flow. So here these are the configurations, and here this is the A. So these are all the magnetic materials. So inside we have, so this is the fluid flow. So inside we have the magnetic material, and this is the magnetic material in this configuration, and this is the magnetic material. So these are the structures of magnetic materials inside the regenerators. So regenerators in magnetic refrigeration, regenerator design, a regenerator that undergoes cyclic heat transfer, and the magnetocaloric effect is known as active magnetic regenerator. In short, it is known as AMR. And AMRs are designed to undergo heat absorption and release during the refrigeration cycle. And design considerations for AMRs, the AMR should possess certain attributes, although these requirements often conflict, making it difficult to design and fabricate. And high heat transfer rate, low pressure drop for the heat transfer field, and a high magnetocaloric effect, sufficient structural integrity, low thermal conduction in the direction of fluid flow, and low porosity, affordable materials, and ease of manufacture. So these are the considerations of AMRs. So types of regenerators. Regenerators consist of various types of geometries to improve heat transfer, and one is tube and perforated plates, wire screens, practical beds. So the figure that we have seen illustrates various type of regenerator design, showing how the fluid flow interacts with the different magnetic materials and their structures. So these designs aim to optimize the heat transfer within the regenerator. The use of superconducting magnets in magnetic refrigeration allows for the generation of strong magnetic fields necessary for cooling processes. So additionally, active magnetic regenerators AMRs are essential for improving efficiency by absorbing and releasing heat. The design of these regenerators must balance several critical factors to achieve optimal performance in magnetic refrigeration systems. So that is the importance of AMRs. Superconducting magnets, the most practical magnetic regenerators are superconducting magnets that operate at cryogenic temperatures around minus 269 degree Celsius or 4 Kelvin, 4 degree Kelvin. These superconducting magnets are electromagnets that conduct electricity with essentially no resistive losses. The most commonly used superconducting materials is made of uh, niobium and titanium alloy, and this is the structure, and we have power supply, and we are giving two superconducting wire coil, and this is the casing, and this is internally the superconducting coil is placed like this, and here insulation layer, insulation chamber. Within this insulation chamber, this material superconducting coil is kept, and the power is supplied, and power supply is given to both terminals of the coil, and this is the superconducting magnet. So magnetic field strength, superconducting magnets can generate very strong magnetic fields. A typical field strength of refrigeration applications is around 8 Tesla, and which is approximately 1,50,000 times the strength of Earth's magnetic field. So an 8 Tesla field can operate a magnetocaloric temperature change of up to 15 degrees Celsius in some rare earth materials. This figure shows the design of superconducting magnetic coil, and the current flowing through the superconducting wire coil inside the insulation chamber. The power supply is used to generate the current, creating the magnetic field. So applications of magnetic refrigeration, a rotary AMR liquefier, and the cryofuel system group is developing an AMR refrigerator specifically for the liquefaction of natural gas, and this technology utilizes a rotary configuration to move the magnetocaloric material into and out of magnetic field for superconducting magnets. The same technology can be extended to liquefaction of hydrogen and system design. In this system, the natural gas enters the unit and is cooled using magnetocaloric effect within the rotating system. As the magnetic material moves through the regions of high and low magnetic fields, it absorbs and releases heat, facilitating the liquefaction of the gas. So here I will show you the diagram. This figure illustrates the system components of the rotary AMR liquefier, including the superconducting magnets, magnetic regenerators, and the heat exchange fluid circulating system. The heat is transferred to the environment or to the refrigerant as required, and the system operates using power input to drive the magnetic wheel. So here applications of magnetic refrigeration, and you can see the heat flow out to environment, and this is the coil, and this is the power input. So power input is given to the magnetic field here, and the high magnetic field region. This is a high magnetic field region, yellow color, and no flow region. So here no flow region here. So this is hot duct is provided here. Again here like a compressor is provided here, and we have another side heat flow in from natural gas, and heat flow out from to the environment. So this is the natural gas in and natural gas out, and this is one application. So here this is gray color, that is superconducting magnets. So gray color objects are superconducting objects. So this one and this one are superconducting magnets, and yellow color magnetic refrigeration wheel. So this yellow color is the magnetic refrigeration wheel, and this is the cold duct, and here this is hot duct, and heat exchange fluid circulating system. So blue color, all blue lines are heat exchange fluid circulating system and wheel driving system. So this is the orange wheel driving system. So this is one of the architecture of its application. So future applications, current limitations. At present, magnetic refrigeration with permanent magnets has not yet reached the level of development needed for practical freezing applications. Large temperature spans between the heat and source and heat sink make such applications less feasible. So that is another drawback. And however, using superconducting magnets could make magnetic refrigeration more viable, and especially in the large refrigeration units. And promising future applications, magnetic household refrigeration applications, magnetic cooling and air conditioning in building and houses, and central cooling systems, the refrigeration in medicine for maintaining vaccines or other sensitive materials, and cooling in food industry and storage, cooling in transportation, refrigerated transport for peripheral goods. So cooling of electronics, so to prevent overheating of advanced computing systems. So there also we can employ this magnetic refrigeration system. So benefits of magnetic refrigeration system. So technical benefits: high efficiency. The magnetocaloric effect is highly reversible, so leading to a high thermodynamic efficiency in the system. So magnetic refrigerators are approximately 50% more efficient than traditional vapor compression systems. So reduced operating cost. Magnetic refrigeration eliminates the most inefficient part of today's refrigerators, the compressor, and reducing overall operating cost. So here there is no compressor involved, that's why it is more reduced operating cost. So it reduces the operating cost. So compactness, due to the solid material used, so gadolinium instead of gases in the refrigeration process, the magnetic refrigeration allows for compact devices. with high energy density. So the absence of gas reduces concerns about emission into the atmosphere, making the technology more reliable compared to traditional systems. So that is reliability of this system. So advantages of magnetic refrigeration system. So advantages over vapor compression and vapor absorption systems, and similar functionality. The magnetic refrigeration performs the same basic function as traditional compression cycle gas refrigeration technology. In both systems, cooling occur by transferring heat from low place to another. So in magnetic refrigeration, gadolinium, a metallic compound, is commonly used with the traditional systems use gases that expand, compress to perform the heat transfer. And environmental benefits. So magnetic refrigeration is viewed as environmentally friendly alternative to conventional vapor compression cycles. It eliminates the need of inefficient compressors and does not involve the use of traditional refrigerants that contribute to ozone depletion. New material advancements. There are many developments taking place. The recent developments in magnetocaloric materials have led to more efficient systems, such as the use of MnFe P0 45AS055 alloys at room temperature, which improve magnetic refrigeration efficiency. So potential advantage. So purchase cost. So purchase cost. While the initial purchase cost of magnetic refrigeration systems may be high, the running costs are significantly lower, often 20% less than conventional chillers. So life cycle cost lower due to reduced maintenance and energy consumption. And ozone depletion refrigerants. The magnetic refrigeration avoids ozone depletion refrigerants, making it more eco-friendly. So energy efficiency, the energy efficiency of magnetic refrigeration is typically 60% to 70% of Carnot cycle efficiency. So it provides very good percentage of Carnot cycle efficiency and offering a substantial energy saving compared to conventional methods. So maintenance free operation. So magnetic refrigeration systems are maintenance free and mechanically simpler when compared to traditional refrigerant based systems. So green technology, the use of solid materials instead of gases make this technology a greener alternative to conventional refrigeration systems. So noise free. Unlike traditional compressors, magnetic refrigeration operates without the need for compressor, making it virtually silent. So compressors obviously produces very huge noise, and that is not there in this case. The compressors are not required for magnetic refrigeration systems, so that is the only reason it is silent in operation. And here making it virtually silent, which is an advantage in noise sensitive environments, examples hospitals or medical applications. So higher efficiency, the thermodynamic cycles used in magnetic refrigeration are close to the Carnot cycle, providing higher efficiency due to reversibility of the magnetocaloric effect MCE. So, simple design, magnetic refrigeration systems like rotary heat exchangers have simpler designs compared to conventional compressors, and low pressure magnetic refrigeration systems can operate under low atmospheric pressure, making the system for use applications such as air conditioning and refrigeration in automobiles. So, initial investment, the higher investment compared to the conventional refrigeration systems due to the use of superconducting materials and other high tech components. So, this is the disadvantage, higher initial investment. So, material availability. So, material availability, magnetocaloric materials used are rare earth materials, so which limits their availability and increases their cost, and development of GMCE materials. So, that is the giant magnetocaloric effect materials. Materials with giant magnetocaloric effects GMCE needs to be further developed to allow for higher frequencies in rotary and rectilinear magnetic refrigerators. So, electromagnetic interference, the protection of electronic components from magnetic fields is a challenge, although this is the mitigated as the fields are typically static and of short range. So, these are the disadvantages of magnetic refrigeration system. And field strength limitations, permanent magnets have limited field strength, while the electromagnets and superconducting magnets are expensive, which adds to the system's overall cost. And temperature change limitations. So, temperature changes in magnetic refrigeration are limited, and multi-stage machines may lose the efficiency due to heat transfer between stages, and precision required. So, moving components in the system need high precision to avoid magnetic field reduction due to gaps between the magnets and the magnetocaloric material. So, these are the disadvantages of magnetic refrigeration system. So, there ends this topic. Now, we have completed the magnetic refrigeration system, and in next class, vortex and pulse tube, both we will discuss. Another two topics left out, we will discuss in coming sessions. We will stop here, students, and these are the references as we see, and you can refer the R.S. Kurmi book. R.S. Kurmi is a better book for this topic. You can refer this book, and also you can refer R.K. Rajput. Rajput is also a very good book. You can refer that book as well. So we stop here, and thank you, students. We will meet again in next session. We will take up the next topic in this unit. We have two more topics to deal in this unit. So we stop here. We will meet again in next session. Thank you, students.